Our previous slide introduced the idea of special relativity. And so special relativity is going at constant speed, and we talked about length contraction and then time dilation. And then at the very end of the presentation, I said there are equations. So yes, the equations. So the equations are for time dilation that the time is equal to T naught. T naught's the actual time that you measure if you're not moving, divided by this factor square root 1 minus V over C squared. Length contraction, same sort of thing, same factor in there, so except it multiplied. And so what does this mean? Well, if you're going very, very slow, V is a small number compared to C. C is the speed of light. That's very, very fast. So most of the time, small number divided by big number is real close to zero. So real close to zero squared is even closer to zero. So 1 minus something really close to zero is really close to 1. Square root of 1 is 1. And so T equals T naught. If you're going very slow, L equals L naught. L naught is how long something is if it's sitting still. T naught is how long something takes if it's sitting still. But what if you're going fast? So if you're going fast, then V over C is a substantial thing. So so if you're going half the speed of light, then V over C is going to be 1/2. 1/2 squared is 1/4. So 1 minus 1/4 is 3/4. Square root of 3/4. So that means that's a little less than 1. So that means T is a little bit longer than T naught. You divide by something less than 1. Likewise, the stuff under the square root is less than 1. So L times something less than 1 is going to be a little bit less than L naught. So that means you get shorter. You get very, very close to the speed of light. And so V is very, very close to C, so that means that V over C is just barely less than 1. So 1 minus something barely less than 1 is going to be barely bigger than 0, or barely off of 0. And so we take the square root, still barely off of 0, so it's just barely, barely positive. And so T naught minus that minus something close to 0 is huge. So that means that while very little time passes for something moving, a whole lot of time passes for something that's sitting stationary. And likewise, the length measured for something moving is going to be much, much, much less than the length measured if it were stationary. Problem comes if V equals C. If V equals C, going the speed of light, then V divided by C would be equal to 1. Be C over C. That's 1. 1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. Well, therein lays a problem, because that means we have T equals T naught over 0. Well, wait, T equals T naught over 0, that's undefined. It's like, what does this mean? It means that basically you can't measure this. Well, if I cross multiply, then 0 times T equals T naught. That means that no matter how long time passes in the universe, 0 times that is 0. So that means that no time at all has passed for something that's moving. Likewise, over here, L naught times 0 is 0, so that means there's no distance. You shrink down to nothing. So if you're moving close to the speed of light, you shrink to nothing in size, and time stops for you. You don't measure any passage of time whatsoever. Light travels with the speed of light, so time doesn't pass for light. And so that means there is no passage of time for light. And so that suggests that as far as light's concerned, it's instantaneously wherever it wants to be. So light leaves the Andromeda galaxy. It takes 2.5 million years to get to us, but light doesn't experience that. As far as light's concerned, it arrives the instant that it leaves. Likewise, because the length contraction, as far as the beam of light is concerned, it doesn't go anywhere. It's not moving. All of space is simultaneously at the same spot, so that you have a beam of light that travels 2.5 million years to get from the Andromeda galaxy to the Milky Way. As far as the light is concerned, it is simultaneously at the beginning point and the ending point and everywhere in between. So all of a sudden, if you were in a spacecraft and you ran to somehow reach the speed of light, then you would simultaneously be at your starting point, your ending point, and every spot in between, and no time would pass. In fact, no time would pass at all, which means you couldn't change. You couldn't speed up, you couldn't slow down, because those require changes, and changes require time passing. So if you're going the speed of light, you can never go anything but the speed of light. Light can't, I mean, something moving the speed of light can only go the speed of light. Something not going the speed of light can't reach the speed of light. And even more so in science fiction, you talk about things going faster than light. Well, you can't go faster than light, because if you go faster than light, then V over C is bigger than 1. Bigger than 1 squared is even bigger. 1 minus something bigger than 1 is negative. Square root of negative, it's undefined. So for all practical purposes, if you were to try to go faster than light, and again, science fiction is like you go backwards in time. No, you don't, because square root of a negative number is not negative. It doesn't mean you're going backwards in time. So it's an imaginary number. So for all practical purposes, if you're going faster than light, you're no longer part of the universe. You're popped out of the universe if you just somehow get there. But something going faster than light can never even interact with anything in the universe, because it's again, space. It's not a negative number here. It's just not a number. And so and physics would say it's orthogonal to the universe, whatever that means. You're perpendicular to the universe, however that works. So this would be a very odd sort of thing. So that means the speed of light is an absolute speed limit. This is not like speed of sound. Whenever I say this, people say, well, yeah, they used to think you could go faster than sound. Well, no, they didn't, because aeronautical engineers were building aircraft in World War II that could reach Mach 1. And in a power dive, they could actually exceed Mach 1. So you actually knew the aircraft were able to go faster than the speed of sound. The problem was controlling the aircraft, because they would reach supersonic speeds and then just keep going until they hit the ground. So they knew they could do it. They just didn't know how to control an aircraft faster than sound. So that was an engineering problem. This is actually a physics problem. This is an absolute speed limit. You may not go faster than the speed of light. Not as part of the universe. Well, E equals mc squared is famous, but it's really, that's the layman's version of it. It's really, if you will go through all the mathematics, which are beyond the level of this class, it's E equals square root of mc squared squared plus pc squared. Now, P is momentum. So the faster you go, the more momentum you have. So that means the energy keeps getting bigger and bigger and bigger. Really, what would happen is, in order to reach the speed of light, you would take an infinite amount of energy, which obviously you can't do. Mass also depends here, because what happens is that the momentum is changing as we go, and so mass effectively changes. So again, going to the mathematics, again, beyond the level of this class, the mass increases here, just like with time dilation. And so the mass is increasing. The faster you go, the more the mass. If you were to actually reach the speed of light, you would have infinitely more mass than you had when you started. The only way you could go the speed of light would be if you started with zero mass, because infinitely times zero mass is not going to be an infinite amount of mass. There's something in mathematics called L'Hopital's rule in calculus that allows you to calculate what 0 over 0 would be. And so it turns out that something going that has no mass, if it's going the speed of light, actually can carry momentum. That's how light carries momentum. But if you have mass to start with, if you go the speed of light, you have infinite momentum. Well, obviously you can't do that. That take infinite amount of energy, and so you can't do that. And then likewise, if you're going faster than light, again, you're taking the square root of a negative number, and so that means your mass is not even real mass. It's not even definable as mass. So basically, you cease to exist. I mean, something going faster than light doesn't exist. And so, once again, this is an introduction here to special relativity and with the equations of it. Relativistic kinetic energy. Again, mathematics shows one once again, that you basically go to infinite energy if you reach the speed of light. Okay, and again, the equations, deriving the equations beyond the level of the class, but I think it's important, even at the level of this class, that you know that there are equations that have been derived to describe all this stuff. And so there we have special relativity. Once again, speed of light is an absolute speed limit.